All right, let's get into it. Today, we're talking about a way to see what's hidden deep inside the materials all around us. We're going to explore how scientists are creating what's basically a unique fingerprint for any material. A fingerprint that can unlock secrets about its structure and even its cosmic origins.
But let me ask you something first. When you look at an image, any image, what do you think you're actually seeing? You'd probably say light, shadow, maybe some colors. And yeah, you're not wrong. But what if I told you there's way more information hiding in there? You see, for scientists to use these incredibly powerful electron microscopes, a simple picture, just the light and dark spots, well, it's just not the whole story. For decades, they've been capturing these amazing images, but they've always known that every single particle that makes up that image is packed with more data that could tell a much deeper story.
And that's really what this is all about. We're going beyond just a pretty picture to get at the hidden data that every single electron is carrying with it. This is where we find out there's so much more than meets the eye.
And this, right here, this is the heart of it. It's not just about if an electron manages to get through a material to light up a spot on the detector. No, the real secret, the good stuff, is in how that electron made the journey. Did it get bumped off course? Did it lose some steam, some energy along the way? Answering those questions, that's the key.
So you can think of it like we're detectives. Every single electron that we fire through our sample, it brings back two critical clues about the material it just passed through. And when we start collecting all these clues, we can piece together a really clear picture of our mystery material.
Okay, so these two clues, they break down pretty simply. First, there's the how many clue. We're basically just counting what percentage of electrons get scattered and miss our detector completely. It's like, imagine you're firing 1,000,000 tennis balls through a dense forest. This clue is just counting how many of them hit a tree and go flying off in some random direction. Then there's the how hard clue. For the electrons that do make it to the detector, we ask, how many of them kept all of their original energy? This is like finding those few perfect tennis balls that zipped through the forest without so much as grazing a single leaf.
So, what happens when we take these two clues, the ones that got through and the ones that got through perfectly, and we plot them against each other? Well, you get something incredibly powerful. You get a unique, totally solid signature for that material at every single point. You get its fingerprint. Now, the official name for this is a zero-loss/deflection map. It's really just a simple, elegant graph that combines our two clues. And what's so brilliant about it is that it paints a clear picture of the material's real properties, like its thickness and what it's made of, in a way that a plain old black and white image never could.
So, how do we actually build this map? It's really just a simple two-axis graph. The horizontal line at the bottom, the x-axis, that's our how many clue. It tracks the fraction of electrons that made it through without getting deflected. The further to the right a point is, the more electrons got through. Then you have the vertical line, the y-axis. That's our how hard clue. It tracks the fraction of those electrons that lost zero energy. The higher up the chart, the more perfect their trip was.
And every good map has landmarks, right? On this one, the top right corner, 0.11, well, that represents a perfect hole in the sample. It means 100% of electrons zipped right through, and 100% of them lost no energy. Easy. The bottom left corner at 00 is the total opposite. That's a spot so thick and dense that zero electrons get through at all. And all the other points, everywhere else on this map, that's the good stuff. Each one is a unique signature of the material's thickness and composition. It's the fingerprint.
Okay, so that's all the theory. But does it actually work in the real world? To find out, scientists took this fingerprint analysis and aimed at a material that had a really complex but known structure.
And this was their first test subject, a bamboo-type multi-walled carbon nanotube. Just picture a bunch of tiny hollow carbon tubes nested inside each other, but with these little walls inside that make it look like a stalk of bamboo. It's actually the perfect test because you've got all these different thicknesses right there in one tiny structure. And, as the researchers themselves pointed out, this thing is perfect because it lets you test your method on parts where you already know exactly how thick it is and how it's oriented. And guess what? It worked. The map perfectly identified the different parts, the hollow middle, the denser walls, those thicker bamboo segments. It proved the whole fingerprint concept was legit.
But now we get to the really mind-blowing part. What if you could use this fingerprint not just on man-made stuff, but to actually read the history of our solar system from a tiny speck of dust that's older than the sun itself?
The next sample was exactly that. It was a microscopic slice taken from the famous Murchison meteorite. And inside that meteorite are these tiny little graphite grains that literally formed in the atmosphere of a dying star, way before our sun and our planets even existed. They are actual, literal stardust, and they're shaped like tiny little onions with a core and an outer rim.
So when the scientists used their fingerprint map on a slice of one of these little graphite onions, wow, the result was instant and it was crystal clear. The map showed a huge difference between the material in the outer layered graphite rim and the unlayered graphium material right at the core. They didn't just look different, they had fundamentally different physical properties.
And get this, the analysis was so sensitive it could put a hard number on that difference. It found that the core had something called an inelastic cross-section that was only about 80% that of the rim. Now, all that cross-section means is basically how big the atoms seem to a passing electron, how likely they are to interact. To measure that difference so precisely on a microscopic bit of ancient stardust, that is just incredible.
And that 80%, that's not just some boring number. It's a clue. It is a message sent to us from across billions of years. It tells a story about the conditions in the universe way back then. It tells us something about how this exact grain of dust was forged in a dying star long before the Earth was even a thing.
Ultimately, what we have here is a new key. A key that can unlock the hidden fingerprints of pretty much everything that makes up our world, from the most advanced technology to the most ancient stardust. And it really just leaves you with one question. What other invisible stories are written inside all the materials around us, just sitting there, waiting for someone to find the right key? Thanks for joining me.